Before I let Kirk on, I'd just like to remind you that there is a sign-up sheet for lightning talks just out there in the corridor in front of one of the workshop rooms. So if you've got an idea for a 5-minute talk or even a 10-minute talk, we'd be glad to have it. So, Kirk, take it away.
Thanks, John. My name's Kirk. I'm here today to talk about kernel testing. Let's see if this works. Yeah. So I'll go a little bit kind of my background first. I'm really excited to be here. I used to live in Dublin, so it's kind of like my second home. So to come here and do this speech today, or my talk, is just amazing. So when I was here, I used to be a Google storage SRE. So I stole this from Wikipedia. I think this is kind of my first job at Google, is carrying the pager for this stuff. This is the Google file system. The point I wanted to make from here is this is kind of complicated. There's multiple machines here. There's probably a node for your app. There's probably multiple machines, one for your master, your shadow masters. I'm hoping your chunk servers are on different machines. That's usually a bad sign when they're not. But there's probably six or seven machines here. My first job was an operating system tester at UNX. They're a real-time operating system company in Ottawa. And I want to say a big contrast. So this is the kind of stuff I would work on here. This is called a Shiva plug. It's an ARM-based platform. It's got 512 meg of RAM. So it's an embedded system. It's a platform people would demo their kind of apps on. It's a whole different space than kind of the cluster stuff. So I guess the point I was trying to make is in the different worlds I've worked in as a tester and as an SRE, scale was a big difference between these two systems. Today I'm back in Ottawa and I'm working at Shopify as a production engineer. So I wanted to tell a quick story how these two job ladders, so like I had this journey from a testing job ladder to an SRE job ladder, and I learned a lot from both, and I feel it was a bit of a fusion. Like I think the jobs are very similar. So I wanted to tell a story how it was similar for me. So this is, again, from Wikipedia. It's a picture of the Unix file descriptor model. And when I was a tester, I liked to exhaust resources and then test the software and see what happens. And file descriptors are a great thing to exhaust to hurt your system and your applications. So I would do that in many of my tests. So when I carried the pager for Google, one of my first pages was to go investigate a sick machine. And I noticed it right away. I said, there's no file descriptors because I've seen systems out of this state. So, it's kind of funny as a tester, you're taking a stable system, making it unstable, and then find bugs and try to get that to never happen again. But as an SRE, I would start with an unstable system, figure out what's going on, get it stable again, and then try to make sure it doesn't happen again. So I always thought it was the same job. I never really noticed that much of a difference, to be fair. All right, I'll jump into the meat of the talk. So these are what I'm going to talk about today. I'm going to define what I think fuzz testing is, at least for the scope of this talk. I'm going to give an example of some classic fuzz testing and why I don't like that style of fuzz testing. So I'll talk about my ideas for a fuzz testing framework, and I'll provide some examples using FreeBSD. So I'll jump into the trends here. So there's actually an IEEE international standard for testing and software development. It's about the size of a telephone book. All the terms in there are very formal sounding. So if you hear like functional testing or unit tests and interface testing, it's all in there and it's very formal sounding. And I found that the testing terms that aren't in that book, they sound very organic and funny, like fuzz and all these other names. So you can really tell if it was part of the standard or not. So this term comes from that standard. It's called non-functional testing. So these are tests that don't relate back to the requirements at all. And it's very broad. It can mean anything that's just not testing requirements. So today I'm going to say that fuzz testing is definitely a non-functional test. Most times when you read a specification for your software, it doesn't say, and it shall not core, right? Everyone just assumes that's the case. So when I do this kind of testing, I'm not really testing back any requirements. So fuzz testing is definitely non-functional. And I'm just attacking the software with a lot of random inputs or random orders of inputs. I think that's really, in a nutshell, what fuzz testing is, at least for this talk. And the last term I wanted to mention was exploratory testing. I'll mention it later on. But I think testing should be automated as much as possible, just like system administration work. But sometimes either you need to debug something or you want to innovate and try something new. So you need to have a manual interface, and you need to have an automated interface. So exploratory testing is a term for just ad-libbing things. So I wanted to add that term in there as well. So this is CrashMe. This is the output what we see when you run it. It's from the early 90s. I downloaded it from Usenet, and that's kind of the GitHub of the day. And what it does is it just takes a random string of bytes and jumps to it. And that's it. And what's expected is that process should core, and then CrashMe will make another one. And that's what it's supposed to do. When I ran it in the early 90s, it would kill every operating system I tried it on in less than 30 seconds. And some of the crashes were you had to reboot. You actually got the machine in some undefined state. So it was quite eye-opening and got me interested in this kind of testing. So one of the problems with this style of fuzz testing is you hit the paradox really fast. So the pesticide paradox is, when you find a new test technique, you find lots of bugs in that area because this code path hasn't been tested before. But as the bugs get fixed, that style of fuzz testing keeps hitting that same path, and you're not going to find the same bugs anymore. And I'm sure you've seen that in your real life. For example, CrashMe has this problem as well. So I guess my only point really here is if I'm going to invest my time to make a new framework, I'm going to try to do something so that it'd be useful for years, not get obsolete very fast. So here's an example of CrashMe I found from the Linux journal a few years ago. They ran CrashMe for 24 hours as part of a release test. So obviously they fixed the code path in there when I used it in the early 90s. But my point for this is the second point, is this is a long time to debug these type of fuzz tests. So let's say there is a 24-hour CrashMe test that you're running, and that's in the first hour the corruption happens, but nothing is asserted on it yet, so there's no panic. And 20 hours later, the assert hits, and then you panic the kernel. So if you're a developer, you might have 20 hours of logs to look through. And I don't think that's going to help you that much. If you do make a fix, you've got to run it for another day. So your cycle of fixing and testing is just too long. I don't think this is really applicable for anybody who wants to do that, especially as a volunteer open source project. So if I'm going to make a new framework, I want to try to resist the paradox. I want the bug to be reproduced in minimal time and minimal code, minimal complexity. I don't want this 20 hours of running time. And it should be really easy that you can add to regression test even before you sort of submit the bug report. Kind of a dream. We'll see what happens. So I was thinking about how to defeat the paradox. And I was thinking, as computer programmers, we're always taught to reduce the complexity of our algorithms. And we just do it naturally now. Maybe we don't consider that increasing the complexity of your algorithm might have an advantage for you. So when I was looking at CrashMe, I kind of thought, well, maybe this is just, big O of n. It's not that complicated. It's just, it's just a sequence of integers, and it's just the, exception path in the kernel. That's it. So I was thinking, if I increase the complexity of the space, would I continue to find more bugs? So sort of my thought experiment, I thought about Mad Libs. And Mad Libs is a kid's game. You take a paragraph of text, and you take the verbs out, and you shuffle them and put them back in the paragraph. And then you read the paragraph, and semantically it's all correct. Or syntactically it's correct, I should say, sorry. Semantically it doesn't mean anything anymore, and kids like this game because they giggle because the paragraph makes most sense. So I considered that approach for testing the kernel. Could I use a Mad Lib approach? And I like testing file systems the best, so I thought about file systems. You can divide this space into two classes. You can have objects that are on that file system, so you can look at the FIFOs, the files, directories. So you have a class of objects. But then you also have sort of a class of operations that work on those objects. So you have the base operations or the kernel calls. You can open, read, dir. And if you mix it up, if you take for every operation, you try it for every object, you kind of have a space that's maybe n squared now. And how I kind of hand wave with that, if you do add another object, you've got n more tests because you're going to run each operation against it at that. So that was kind of my theory that this might be more complicated and maybe be a larger space to test. So I wanted to give an example of this Mad Lib idea. And this panicked FreeBSD6. What's happening is you're making a name pipe on disk and you're trying to truncate it. And this would panic the kernel. Usually the first question I get with this is people are thinking functional. So this is a non-functional test. I don't care what this does, as long as it doesn't panic the kernel. But the first question I get is a functional question is, what is it supposed to do? And the funny part is no one knows. POSIX, this is one of the famous POSIX undefined or unspecified statements. So I guess technically if you panic here, you still have a POSIX kernel. It's just not very useful. So I'll try to talk about what I'm actually trying to fuzz, because that's usually the next question. So I guess my spin on fuzzing is that I don't like doing exceptional cases. I find that if you have kernel developers don't like it if you have cases that are too exceptional. So what I started with for this test suite anyways, is let's say you ran dtrace on your kernel and you captured every kernel call that was happening on that system and all the objects it was acting on. What I would shuffle is just all those kernel calls in a different order that were already valid, they're kind of been run, and all the objects people were using, I would shuffle them. So there's nothing too sinister going on. I'm just pretending I'm a user doing things in random orders. So I'll just go through this one more time, make sure I got it. So I'm just changing the ordering of the kernel calls, and then I'm taking all my objects, and of course I'm shuffling for each kernel call and doing the objects in different orders. And the set of kernel calls. I might not run all the operations. I might choose to exclude an operation or just use a smaller subset of operations. Sometimes that actually will cause a panic. So I'll give a list of operations. They're not always kernel calls. Sometimes I do more complicated things in an operation. So definitely every kernel call could be an operation. Sparse files are a hidden object on the BSD file system. A sparse file appears to be a file of zeros, but it really isn't. So that's a good object to add to your list because you want all your calls to hit it again. gcore is kind of amazing, and I don't know why. I only have a theory. Calling gcore a lot tends to panic the kernel. My theory is, since it's writing a process to disk, it's probably traversing a bunch of data structures and maybe calling the asserts. So maybe it just kind of ends up calling a lot of panics by accident because it's hitting those code. That's my theory, anyways. Open's the best call in the universe to test when you're a fuzz tester. It's got so many flags and combinations, it's wonderful. Especially for new file system developers, calling trunk in a directory, I've corrupted many file systems with that. Again, that's another unspecified thing that POSIX has left us. Mmap, I try to minimize my use of it. It confuses people. When you mmap in a file and you shrink the file size object, you still have that space mapped in it. You get a sig bus, and it tends to find, you debug it and you realize, oh yeah, it's just the changing of the mapping. So I just went to the utilities and found what they were doing. So I copied sort of the use cases of AR, CP, and file in it. So just very simple uses of mmap. Yeah, you should be a bit skeptical now. In the beginning, I talked about I want to make this easy for the devs and have minimal runtime. And now I just talked about increasing the complexity and introduce this Mad Libs, like how I'm supposed to make this easier for developers. So basically, I think we just should start with a new framework. So I'll walk through sort of a life cycle. I think the first time when you start, you just make spaghetti code. You're just going to code up. You get 1,000 lines of C, you panic the kernel, it takes 8 hours. You think the kernel developer is going to be happy, but not so much. So the first abstraction I usually see is you try to take the execution and you abstract that out. I think the testers are happy with this. I think it's easier to write fuzz tests when you have an API. But I think at the end of the day, it doesn't help the kernel developer because they're probably going to have to look at the big picture anyways. So I don't think this is really a good model. So I thought the next step was to really get hardcore, and instead of having an API, make a real data set implementation for the fuzzing. So you write a program that's the fuzz generator, and it doesn't do anything, but it just creates a data set of what operations and objects should be run. And then later on, you take the executor that takes a file, and it will run those things in the random order. So they're totally two different programs now. And this is supposed to be a joke, but this is the Unix philosophy. So all I'm really doing is taking the Unix philosophy that's worked for probably 40 years and do it for testing. Is, you know, write one program, do it well, and use text in between. So I think where the magic comes in now is now I can do my exploratory testing. So, you know, I can create my data set, but it doesn't have to be the same data set I execute or give to the developer. I can write a modifier and filter now on this data set to do something to it. I can delete an operation. I can try to make it a minimal set. It's up to your imagination what you need to do to change your data set so that it's easier to either add to your regression test or reproduce the bug. So this is one of my first ideas to try to automate this a little better, or my first idea of a modifier was kind of this competition. So let's say you have 100 operations to start with in your sort of your library. My idea was to sort them and split them into different data sets. So every operation's in one data set, not both. So you'd have 50, and you just run them in parallel and see what happens. And what you're hoping for is a panic. And if you don't, you just reshuffle and try it again. So, you know, this would work in a cluster. You could run many of these things at the same time. So that was kind of my first idea. And if you do get a panic, that's kind of exciting because you're not using 50 operations. So you've kind of already reduced the complexity in half of kind of the set that you're playing with. Yeah, I think I just talked about that. I want to go over the term competition and champion I just mentioned kind of in the previous slide. Why I kind of call it that with this split in the 50-50 is you're trying to converge on a lucky or a very sort of dominant kernel panic. You're not going to find them all initially, so it's a bit of a game you're playing and you're looking for a champion. And I wanted to make that point, for example, if you're using the style of testing as sort of like an acceptance test, that's not really a good idea. You're not going to find all the panics. And even if you don't find a panic, it doesn't mean there is one. All I'm trying to do is play a game and try to find a very dominant bug very fast. All right, so I talked about all these theories I've been hand-waving. I wanted to show an example of some of these ideas that I did with FreeBSD. So 6 years ago, I attended a conference in Ottawa. Dr. McCusick presented a paper about adding some journaling features to the traditional BSD file system. The idea was he wanted to reduce the running of fsec after a normal reboot. He just wanted to do some journal magic. I kind of daydreamed during this talk. I actually told him as much, to be fair. But it's actually hard testing new file system ideas when you test a file system that kind of works. It gets really boring really fast. So I was thinking, he added this feature. It sounds complicated to me. There's got to be a bug here, right? So I wonder if it would be a good example to play with my new testing ideas. So when I got home, I started coding up sort of my framework idea. So the first one is I did keep the Mad Lib approach, operations versus the objects. I didn't do a data set to start with. So my plan of attack was to write a few operations, run it overnight, and just keep going until I panicked the kernel. And eventually I did it. When I got to 100 operations, the kernel started panicking overnight after 8 hours of testing with this framework. So that's pretty cool. I removed the journaling feature, and I was not able to reproduce the bug. So I'm assuming it's a bug in Dr. McCusick's new code. So I think I sound a bit more, but I'm really excited I find bugs in someone's work. I'm sure Dr. McCusick and whoever worked in this feature weren't intending to add this bug. So, but to me it's exciting because it helps my research. But I guess I kind of proved Dijkstra correct, is unfortunately coding does add bugs, and that's why we have to do this kind of stuff. So now I've got my panic. I'm going to start using my data set idea and see what I can do with this. So I started with my first idea, doing the competition. So I had 100 operations. I split them to 2 data sets of 50, run it overnight and see what happens. Yeah, and very quickly I did get a champion. One of these archives, or one of these data sets of 50 did panic the kernel. So I decided to try it again. 2 archives of 25, run it overnight, what happens? Yes. One of these data sets panicked the kernel. So keep going. So I have an archive of 12 and 13. I try it again, and I think the 12 data set won. So that's pretty cool. And now the execution time is 5 minutes now. It's no longer 8 hours. And I've already got rid of 90 plus operations. This is pretty awesome. I'm not sure why I can reduce it anymore. The archives of 6, I tried a few times, I couldn't get a panic out of them. So I've experimented by just seeding in a bug. So if I just put like dereferencing and outpolling in the kernel in a random spot, I'm able to divide and conquer right down to the kernel call that's causing it. So that this algorithm will go right to the culprit if it can. Since it's not getting any farther here, my guess is this is a complicated bug and it involves multiple kernel calls. So I think that's one of the advantages of the Mad Libs and my approach at fuzzing, is I've seen other kernel fuzzes where they focus on one kernel call and just keep putting invalid data in that one kernel call, but they're not going to get the state of multiple kernel calls. My algorithm here will get, if there's state, we're going to find it, I think. So I wanted to keep trying. Could that be, I think, is that a good enough bug report saying 5 minutes? I think so. I think that's much better than 8 hours. But I wanted to keep experimenting and see if I can make different filters and try again. So I was thinking, since I only had 12 operations and it's taking 5 minutes, the different approach was, so in the past, we were competing against sets of operations against each other. I was wondering, can I compete each operation individually against each other? So what I plan to do is to make 12 different data sets, and they'll have 11 operations each. So I'm deleting one operation and just seeing what happens. That's what I was going to do. So this is the first kind of iteration of this. I've removed operation number 1, and I run this data set. And what happened was this data set did not panic the kernel. So my guess is that operation number 1, it's a culprit. It's important. The absence of this one, you can't reproduce the panic. So 1's a good guy. So I want to remember that 1's important. So I'll try my next iteration. I've got 11 operations again. I'm removing number 2. And the panic happens right away, within 5 minutes. So I'm going to make the conclusion that number 2 is a no operation. It doesn't make any sense. It's not part of the equation of the magic that's causing this kernel to panic. So there's only 12 choices, only 12 sort of combinations to go through. I ran them all. And I think the magic numbers were 1, 3, 4, and 9, I think. So these ones are culprits. These guys are causing the panic. The rest of them are just operations that just happen to get in this last sort of competition. So I kind of wanted to try again. So I took this magic data set, I ran it, and sure enough, I can panic the kernel now in 30 seconds with 4 operations. So I've deleted 8 hours of runtime and 96 of the operations. So I'll just go through what happened here. So the first thing I want to do is I wanted to look at the kernel calls, and I want to see if it passes the complexity test. Like, can I kind of see what's going on? I think the cool part, so I think part of it is, I think when you go to a developer who's written a new feature and you kind of mention your bug, I think they're going to use their intuition and go, oh, that case, I didn't think of that. And that's going to help them get this bug fixed faster. If you go to them with additional fuzz tests and say it takes 8 hours, you've lost this intuition. So I wanted to see if I can make some guesses of what this is doing. So I think open and write is just creating regular file system objects. That's fine. I don't know why G-core's there, but as I said, it seems to be magic. I think it's just creating files in this case. I don't think it's really actually causing any extra panics. I'm not sure what the link is there for, but the unlink and missing the close is the magic here. What's happening is this is turning to a long-lived daemon that's creating a file with a link count of 0 and is keeping the FD open forever. And this is, so if you reboot Unix spontaneously and you run fsic, it's going to go delete that file. But with his new feature, he's planning to use some journal magic to do that. So he needs to track these objects. So that kind of makes sense that this bug would happen with this new feature. So that's pretty cool. To submit my bug, I think this is the right state of a bug I'd like to give them. I couldn't just give them my framework, or I guess I could have. I thought it would be too complicated to give them my framework. So I just wrote a modifier that took these 4 ops and converted them to a big C file, and I submitted that to the bug report to the FreeBSD folks. They were able to fix it and add it to regression tests, so that was pretty cool. So I'm just going to close up and sort of give sort of my lessons and try to rope this back into why SREs might be interested in this, or some lessons. So one thing I wanted to mention is that I don't think I would have had some of these ideas if I wasn't an SRE. Definitely the cluster stuff and the data sets and all this idea. Like, I think that came from my experiences working with clusters. And I was just lucky enough to go back and try with my testing stuff. I think during the SRE panel on the first day, I think it was Joy, she was mentioning that when she hires an SRE team, she tries to get people of different skill sets. I think that's really important. Being a tester on an SRE team, I think I added value. So that's one thing I want to mention is that either, hiring different people or changing job ladders now and then, I think it's a good idea. I think the SRE philosophy of treating everything as a software problem, I think can go to any software engineering discipline. Testers are also stuck with toil and, sort of boring work, and they should try to automate it too. I wanted to talk, this one, I think this talk I focused on technology. I think this talk could easily have been talking about people as well. So like one thing I wanted to mention was, this stuff is not difficult software-wise, it's difficult people-wise. If you're gonna go to your team and you have a new testing idea or a new automation idea that's revolutionary, they're gonna say no, because they don't get it. Like some of the comments I've had in the past with this kind of stuff is fuzz testing is not valid because it doesn't test use cases the customer would use, so those bugs, we don't fix those bugs, right? I've had those arguments. And the same thing with the cluster. I've had arguments in the past, this is a long time ago, but I've had people come to me saying, cluster time is too expensive, there's no way we would run tests in a cluster. And today that's not true. I'm sure everyone runs tests in clusters. But that's the first feedback. It's like Bill Gates and Microsoft making his comment that no program would need more than 640K. It's the first time we always push back on new ideas. So I think this could have been a people talk. Like you have to be a bit of an entrepreneur, or you have to be like your own startup, and you have to find your key customer that's going to use your idea. So I think that could almost be a talk in itself, and I had to do those kind of things to get this stuff going. So that's my sort of trying to loop it back to SRE and the lessons all I had from this. That's it. I'm a few minutes early. I hope you have some questions. Oh, you're letting me off the hook.
Thank you very much.
All right. Yeah, thank you.